Hello, everyone, and welcome to today's Bite of Science webinar presented by the Teacher Enrichment Program of the Center for Excellence in Education. My name is Shannon Tyler, and I am the Teacher Enrichment Program Manager. I will be hosting today's webinar titled Astronomy in the Classroom. We are very excited to hear from today's speaker, so let's get started. To begin, I'm going to share some brief background information on our organization. The Center for Excellence in Education was founded in 1983 by Joanne DeGennaro and Admiral Rickover, the father of the nuclear navy, in civilian uses of nuclear power, with a mission to nurture high school and university scholars to careers of excellence and leadership in STEM. We have cost-free programs for teachers and students, including the Research Science Institute, RSI, the USA Bio-Olympiad, USABO, the Teacher Enrichment Program, TEP, and STEM Lyceum. So first we have the Research Science Institute, RSI, which is a highly competitive 6-week summer science and engineering program open to rising high school seniors and juniors are eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. Next, we have the USA Bio-Olympiad, or USABO, which is the premier biology competition for high school students in the United States. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competition. A fun fact about the USABO is that since CEE began administering it in 2003, every member of the USA Bio-Olympiad team has medaled at the International Biology Olympiad. Next, we have the Teacher Enrichment Program, or TEP, which is the program bringing this webinar to you all today. TEP provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for you and your student. Next, we have our newest initiative at CEE, STEM Lyceums. I'm partnered today with Rebecca Carter. She is the manager for STEM Lyceums, and she's going to be running the background of our webinar today. So thank you, Rebecca. But STEM Lyceums is a virtual club for high school students to engage in discussions and exploration of STEM and to learn about STEM career pathways from leading field experts. Before I introduce our speaker, I would like to encourage you all to take notes while you listen and to ask questions. Please submit your questions through the Q&A function or in the chat, and they will be addressed by our speaker at the end of the presentation. Now, I'm happy to introduce today's speaker, Dr. Eric B. Ford. Dr. Ford is a distinguished professor of astronomy and astrophysics at the Pennsylvania State University, where he is the director of the Center for Exoplanets and Habitable Worlds. He was a student at CEE's Research Science Institute in 1995 and served as a tutor for RSI in 1999. He earned a bachelor's degree in physics and mathematics at MIT in 1999 and a doctoral degree in astrophysical sciences at Princeton in 2003. Prior to joining Penn State, Dr. Ford was a Miller Research Fellow at the University of California, Berkeley, a NASA Hubble Fellow at the Harvard-Smithsonian Center for Astrophysics, and a faculty member at the University of Florida. Dr. Ford's research centers around exoplanets with long-term goals of improving our understanding of planet formation and the dynamical evolution of planetary systems. His research group includes both theoretical modeling of planetary systems and interpretation of exoplanet observations. He emphasizes the interface between theory and observation, including techniques for characterizing extrasolar planets, the statistical analysis of extrasolar planet observations, methodology for exoplanet demographics, and the efficient design of extrasolar planet surveys. He has collaborated with leading planet surveys such as NASA's Kepler mission, the Habitable Zone Planet Finder, and NEWIT team. Dr. Ford's research aims to improve our understanding of the formation and evolution of planetary systems to provide context for understanding our own solar system. His research has been published in over 200 scientific journal articles. Thank you to Dr. Ford for joining us today, and we look forward to hearing your presentation.
So thank you very much for the introduction and the chance to share some of the research we do here at Penn State Center for Habitable Worlds with the CEE Teachers Program. So planet formation is a complex process. It happens very quickly on astronomical timescales. So even though the solar system is billions of years old, the birth of the planets occurs in just the first few million years. And during that time, there's a lot of gas and dust that's enshrouding the planets and the star that they orbit, and therefore it's difficult to peer into the system and see what's happening. We're able to see the outcome of planet formation. We look at mature planetary systems, but it's very hard to study the beginning stage. And so this has been a long-standing problem and has motivated work on theoretical modeling to try to understand, based on physical principles, how planets begin to form in that dusty environment that we can't see through. So we have interesting models of planet formation, but now how do we evaluate them? How do we verify what they're able to do accurately? It'd be nice if we could compare the predictions of our models to actual observations. And so we have several sort of thrusts. One is to work on planet formation. And another motivating factor for NASA and maybe the public at large is there's this idea we'd eventually like to discover and characterize potentially habitable planets, ones that might be able to support life on them and be able to learn about those. So if we want to do that, that's going to take some real effort. And before I dive into some of the methods we're using, I think I'll say what I'm not going to be talking about. Because very often when we think of discovering a planet, we might think that you're going to see it. And it's extra confusing because there actually are planets where we have direct images. So in this case, the 3 little dots orbiting around there, we can make it play again, actually 4 dots in this case, are actual planets. And these are very massive planets, much more massive than Jupiter, much further from their star than Jupiter's from our star, too cold to support life. But there are these directly imaged planets. And so you may have heard and seen some of the exciting discoveries there. But right now, the technical capabilities for imaging other planets is restricted to these very massive stars at large separation. So I'm going to say that's a subject for another talk. What we're thinking of in this context are smaller planets, rocky planets with maybe a thin atmosphere similar to the Earth. And for those, it's going to take a new generation of NASA missions to be able to observe those. And so right now, people are in the early stages of planning for a mission, tentatively slotted for the 2040s. So on one hand, several years off. On the other hand, to actually launch a mission in the 2040s, we need to be planning for it now. And so we hope to eventually have the capability to recognize these potentially Earth-like planets around maybe 100 stars in the nearby solar neighborhood. And to do that's going to require a telescope that's significantly more massive or larger than the space telescopes we have now. And so there's this question of, well, how large of a space telescope do we build? Obviously, astronomers might like it to be as large as possible, but that creates an enormous cost challenge. And so you want it to make sure you build it big enough that you can study several planetary systems, and yet small enough that you don't make it unnecessarily expensive. And even once you've picked a space telescope, you have to know when and where it should look. If we have to do a blind survey with a space telescope, then you lose a lot of the time early in the mission to just looking at nothing, trying to hope you discover a planet. Whereas if we could know specific target stars that had planets and when they would be visible, we could get a lot more value out of that space telescope. And so those two questions are going to motivate some of these surveys to ask how common are Earth-like planets and try to find some of the nearby ones. So I mentioned one of the first order questions is how big of a space telescope do we need to build? And so the sort of scale here, the Hubble Space Telescope that we are familiar with many exciting pictures from is in the bottom left there. More recently, you've probably seen some exciting announcements from the James Webb Space Telescope, significantly larger than Hubble. The designs being talked about for this next generation of telescope range from a little bit larger than James Webb, but with a different design optimized for planet hunting, to significantly larger than James Webb. And at the moment, we have sort of some notional size in the middle that's a baseline plan that people are starting to plan towards, but the reality is we don't quite know if that's going to be big enough to meet the goal of the National Academy of Sciences recommendation to have 25 potentially Earth-like planets as our goal to be able to study. So we want to go for a couple dozen of them. How big does it need to be? And so the first question is, well, how common are Earth-sized planets? These telescopes are able to study the nearest stars much better than the further stars. The further you go away, the larger you need to make your telescope. And so there's a population of maybe 40, 80, 100 stars that we could study, but being able to go from 40 to 80 almost doubles the size of the telescope you need. And so we want to understand, could we get away with just studying those nearest 40, or do we need to go all the way to 100, 120? And that's going to come down to how common are these Earth-sized planets in the habitable zones of nearby stars. If they're very common, then maybe we can get away with just looking at the closest stars. If they're relatively rare, then we may need a larger telescope that's going to delay things from the baseline plan. So in order to start nipping away at this question, NASA launched the Kepler Space Telescope, and its primary mission goal was to understand how common are Earth-sized planets. So how did it tackle that? Well, the Kepler Space Telescope stared at one patch of sky, a big patch of sky, but still, I mean, you could cover it with your hand, right? So a patch of the sky up in Cygnus, a little bit of Lyra, and it stared at that same patch of sky for almost 3.5 years. So every image, it looks like this one. You wouldn't notice a difference. But if you zoom in on this image, you can see that kind of the fuzz is actually a whole lot of stars. On the upper right, we have a somewhat non-representative sample of a fun star cluster, so you have something to see. On the left, maybe a more representative sample, a lot of stars in the Milky Way galaxy, and just lots of dots of lights. And each one of those is a possible target. The spacecraft was orbiting around the sun and was getting further and further away, and so we were limited by how much data could be sent back. So unfortunately, we don't have all these pixels at every instant in time. Rather, Kepler accumulated data for roughly half a minute or 30 minutes at a time, and then was able to relay back little postage stamps around each of about 160,000 stars at once. They swapped some through, so we got a little over 190,000 targets over the course of the mission. We're able to study the brightness of each star as a function of time. So let's see if I can make the movie work. So how does that work? The plan was, if there's a planet orbiting a star, then as the planet passes in front of the star, there's a shadow from the planet that passes over Earth or the Kepler Space Telescope, and we see a little bit less light when the planet is in front of the star than when it's not in front of the star. And we call that a light curve. We apply the brightness of the star versus time, and looking to see if the light curve shows repeated dips due to planets passing in front of their host stars. Of course, this doesn't work all the time, right? So every now and then we are fortunate to be able to see a planet passing in front of the star, but 99% of the time it's not passing in front of that star. And for every one planetary system where we see an Earth passing in front of a sun, there's 100, 200 more where they must have the same size and separation of the planet, but they're just oriented in space in a way that we're not in the line of sight. And so from our point of view, we never see the planet passing in front of their star. And so for that reason, we had to look at a lot of stars to be able to figure out how common these Earth-like planets. So one of the many projects from this Kepler mission was trying to understand the frequency of Earth-sized planets, or planets really as a function of their orbital size and orbital period. And here's one of the fun plots made by Dan Lee Sue, one of the former graduate students from my research group, where we were trying to address this question. And some of the challenges we faced were things like, we know most of the transiting planets most of the planets aren't visible as transits to us because of geometry, so we had to correct the geometric factors. That's actually one of the easiest corrections in the process. Also, the smaller the planet becomes, the smaller the signal and the less likely we are to detect it. And the longer the orbital period of the planet, the fewer times it will pass in front of the stars, the more likely we get unlucky. Maybe in terms of when the spacecraft was beaming data back to Earth, it was looking in the other direction. Maybe in terms of some extra noise due to some spacecraft issues. And so what you can see is if we pick planets that are really close to the size of the Earth, over here on the horizontal axis, and we go out to orbital periods of 365 days, it's in these gray boxes where we have upper limits. So we can say they're not so common that we detected many of them with the Kepler mission. There's maybe a few detections in that corner of parameter space, but the uncertainties are still quite large. And so what this means is we can give you a minimum size for the telescope you need, but we can't yet give you a maximum. So it's kind of disappointing in that aspect, but Kepler was really revolutionary in many ways because we learned about so many more things. So, well, asking for an Earth-sized planet is a natural thing to ask for as someone living on Earth. What about two Earth radius planets? Well, in the solar system, there are none, right? And so you might even have thought there's no need to ask about them because in the solar system, there are the rocky planets that are up to the size of Earth, and there are the giant planets that start at the size of Uranus and Neptune and go up to Jupiter and Saturn, and there's nothing in the middle. And so one of the exciting things Kepler taught us was that these planets between, say, 1.5 to 2.5 Earth radii are actually much more common in our solar system, or in our Milky Way galaxy, than they are in the solar system where we have none. And so some of the most common planets that we know of are not in the solar system. And so if we want to learn about them, we have to go beyond our solar system to study these other planetary systems. And that has created lots of new opportunities for astronomers to study these new interesting types of planetary systems. So what are some of the things that we learned from the Kepler mission? One is that planets orbit sun-like stars quite frequently. There are more planets around sun-like stars than there are sun-like stars in the galaxy. We know that small, presumably rocky planets, even though we've never actually directly determined that they're rocky, but given their size and masses based on physics and geochemistry, we expect them to be primarily rocky with only a tenuous atmosphere, maybe an ocean like the Earth, but fundamentally rocky as opposed to something like Saturn or Neptune, where it's mostly gas with a core that we have no chance of seeing. And so we know those are much more common. That's exciting because those planets are the types of things where we could characterize their atmospheres, their surfaces, their oceans based on photons coming from that planetary system. And we've done our best to try to estimate the rate of Earth-sized planets, maybe a little bit bigger, a little bit smaller. And here the rate I give goes all the way from 3 days out to 300 days. So at those inner orbital periods of just a few days, they would be too hot to support life as we know it. But by the time you're in the outer region, you're able to have climates potentially similar to the Earth. So I know those planets are fairly common, right? FGK stars, and that inspires us to try to go look to find specific ones. Another somewhat surprising legacy of the Kepler mission was when Kepler launched, we thought we were going to find small planets at orbits similar to Venus and Earth, and those would be so rare that they would transit because, again, the separation to stellar size ratio is so extreme that we wouldn't be able to see very often two planets in the same planetary system. So for our own solar system, the vast majority of viewing angles, you would only see one planet transit. You wouldn't be able to see two, let alone 3, 4. There's no viewing geometry where you would see 3 at the moment, and 4 or 5 are just off the table. But for these planetary systems, other stars, they're so compact. The ones we've discovered in abundance are much closer to their star, their own solar system. And also many of them have very nearly coplanar orbits, so that the orbital planes of those solar systems are even more aligned than our own solar system, allowing us to detect not just one planet per star, but 2, 3, 4, in some cases 5, 6, 7 planets around a host star. And that's really exciting because then we get to compare the planets to the planetary system and use things like what's the ratio of their periods and sizes to learn not just about planets as butterfly collecting, but as planetary systems, where the extra information really helps us learn about the planet formation processes that were happening there. So what are the types of things we can learn from a star where we have multiple transiting planets? Well, the first is just how many planets we're able to detect. Right, so if there's only 2 planets per star, we're never going to detect 3. Now, if there's 8 planets per star, then sometimes we'll find 1 of them. Sometimes we'll find 2. Sometimes we'll find 3. And so there's, again, a very complicated inverse problem trying to link the observations, which are strongly biased by, in this case, just simple geometry, to the actual observations. And so that's something we can try to apply geometric corrections for. Another really exciting observation is that some of these planetary systems are really closely packed together. So if we look at the ratio of nearby planets, we can look at their orbital periods and see what are those ratios, their orbital periods. There are some widely spaced planets, but for every one that's spaced more than a factor of 4, there are many that are spaced 3 by a factor of 2, or even 1.5, or 4 to 5, 4 to 3, some very closely spaced planetary systems. One's even as close to 7 to 6. And so those period ratios mean that they're closely spaced, they're interacting gravitationally in interesting ways that probably tell us about how the system's formed. And some of them are interacting strongly enough that we're able to see the planet-planets mutual gravitational interactions and not just a collection of planets that are so widely spaced they ignore each other in their orbit. There's some interesting excesses near obvious integer ratios, 3 to 2, 2 to 1, that point to the role of what we know as mean motion resonances, so where the orbits of 2 planets are nearly synchronized, and that creates the opportunity for the gravitational interactions to accumulate over longer timescales and have more substantial impacts on their planetaries. We can also look at how much light is blocked by each planet and compare those two, and that gives us information about the size ratios of the planets. Now, I told you we could learn the size already, and that's true, but to get a planet size, we need to have both the observational evidence of how much light is blocked, but we also need to know the star size. And oftentimes, our uncertainty in the size of a planet is dominated by our uncertainty in the size of the star. But in these cases where we have multiple planets transiting the same star, we're able to have that uncertainty in the star's rays cancels out. And so we have much more precise measurements of their relative radii than of the individual planetary radii. And so in some cases we can say, well, we can tell here that we have two planets that have very similar radii, but significantly different masses, or vice versa. Looking at closely spaced planets, how common are their size ratios very similar versus disparate? And then there's another observable, which is how long does it take the planet to cross the sun or star? And so there it's interesting because, again, geometry comes into play. Sometimes a planet goes across the diameter of a star. Sometimes it takes a shorter chord. But that's something you can estimate with geometry. And so we can use the distribution of those transit durations as a probe of other orbital properties, such as the inclinations and eccentricities, or how non-circular the orbits of them are. And so while we can't see that individually for most of these planets, we do have information as a population about how often they have nearly circular orbits like the Earth and Venus, and how often they might have more eccentric orbits like Mercury, or even more extreme. Many of the researchers in my research group have contributed to this. What began as a 1 graduate student project became a 4 graduate student, 2 postdoc project to really see this to completion. It's very typical the way science works. You have a vision and it sounds like a fun little project, but as you dive deeper and deeper, you find it gets more and more complicated, and it took a lot of work to be able to make some of the inferences we've been able to make recently. So one of the key adds of the research from my research group was a lot of the early work focused on how many planets are there per star. And you can think of this as you take all the planets Kepler discovered, you put them in the numerator, you take all the stars you look at, you put them in the denominator, you worry about various corrections for completeness, and you get out a number of planets per star. And that's useful if you want to ask a question like, how many planets are in the galaxy? But if you want to plan a mission that's going to look at 20, 40 stars, it matters a lot whether those planets are concentrated around a few stars or whether they're spread out over all the stars, right? So if they're spread evenly across many stars, you can look at a population of stars and be confident you'll have, oh, there's one around each star, and so everyone will have one, and I can have a smaller sample size than if they're clustered and a small fraction of stars have many planets. And so the challenge here is that when Kepler launched, we presumed that we would likely see 1 planet per star would be a success if we were able to see that. And we assumed we wouldn't see very often multiple planets around one star. That belief was so strong that when I wrote some of the early proposals suggesting we try to use this information, the proposals got rejected because that was so unlikely that we would find any of them. And again, you make the arguments of why it's possible, there's some chance, it could be very interesting. It's like, no, it's too unlikely, we won't see any. And only once you actually had the detections were people willing to say, okay, now that we actually see there are stars where we know there are multiple transiting planets, now are we willing to invest some resources in trying to characterize these planetary systems. And so it really was a little bit of luck and a little bit of nature being kind to us that we're able to study these densely packed interplanetary systems. And that gives us a lot of information about the processes that form these planetary systems. When we started doing this, we developed some models to try to explain the planet formation, and we thought we were doing great getting the models down to very fast, 10 seconds instead of days of calculations. And so what we would do is we would generate simulated catalogs of all the planets, and then we would simulate the observing process, the Kepler mission of the geometry and the detection probability and the orbital periods to look at what we would observe if that was the actual distribution of planets in the Milky Way. And then we compare those data to the observations to try to rule out or constrain the model parameters, reject some models, and find others that are consistent with the data. In the process of doing this, it was extremely painful early on, and we had to use some machine learning, or now we brand them as artificial intelligence, I guess, techniques, where we say we have some slow models of planet formation, and then we use advanced machine learning techniques to accelerate the process of saying, let's kind of take shortcuts, and instead of doing all the individual calculations, go directly from the model parameters to the distance between a set of observations from Kepler and a set of simulated observations from our modeling process. And that allowed us to speed things up by a few orders of magnitude, and it allowed us to go from doing the forward problem to doing the inverse problem, where we consider a wide swath of possible models to see what's consistent with the data. And in particular, one of the things we found was that the planets around a star are not drawn independently from each other. It's not just taking all the stars in the Milky Way and kind of randomly assigning them different star labels, but rather we can assess this with the significance of how often are these planets clustered, either in which star they're orbiting, what their orbital periods around that star are, and having similar periods of planets within one of these clusters. And so there were early hints at it for many different researchers, but to be able to establish things statistically significant way and quantify them was one of the real contributions of Matthias and the rest of our research group in trying to understand this and translate it to constraints on planet formation model. And indeed, that's what we found the Milky Way tends to have. And so if I say, what do we learn from Kepler beyond just the original goal of the rate of planets per star? We now know that about half of sun-like stars host an interplanetary system, so say less than 300 days. So planets packed in there, and most of those are larger than the Earth, most of the known planets, that is. And so what we can say is we don't know whether our solar system is common or rare yet. We don't have enough statistics to be able to say that. But what we can say is that most stars make planetary systems that are qualitatively different than our solar system. The abundance of these 2-3 Earth radii planets is so high that the solar system is atypical by virtue of not having one close to its host star. And so that kind of helps us think a little bit about, okay, well, we don't know if we're rare, but we do know we're not the majority. And that helps set the stage for thinking about what planet formation models need to be able to explain. So that's helped us address the question of how large a space telescope do we need to build. We know that with the sizes they're being talked about now, we'd find some pretty cool stuff. We're not sure if we'd reach true Earth analogs, but we know we'd find lots of exciting planetary systems. The next question is, well, can we help it out by knowing when to look where? And so as a follow-on to the Kepler mission, NASA launched the TESS mission. And so this Transiting Exoplanet Survey satellite takes a very different strategy. Instead of looking at one patch of the sky for several years, every month or so it moves on to a different patch of sky. And now it's been going around long enough, it's starting to overlap and go back to some patches multiple times. But the main advantage here is, even though we don't characterize any one patch of sky as well, we're able to survey the entire sky, looking for nearby stars that are easier to study in other ways. What other ways might we want to study these stars with? Well, so far I've talked about one of the primary transit detection or planet detection methods, the transit method, but another very pivotal discovery method is using the Doppler technique. So here you have the Doppler effect. Instead of being sound where you have the ambulance go by, you have the Doppler effect being applied to light, and so we are able to measure these Doppler shifts of the stellar starlight due to the gravitational tug of the planets going around them. The shifts here are, of course, greatly exaggerated. The signals we're looking at for an Earth-sized planet are causing the light to shift on the detector by just a few silicon atoms, thousandth of a pixel, so a very small signal we're aiming to be able to detect, and that's what makes it both challenging and fun. So here at Penn State, the Center for Exoplanets and Habitable Worlds has led the construction operation of two of the current generation of planet hunting spectrographs. Infrared instrument at the Hobby-Eberly telescope in West Texas, the Habitable Zone Planet Finder, and the NUID spectrograph at the WIN telescope at Peak Observatory, focusing on optical wavelengths. And so these two instruments, very similar in design, but optimized for cooler stars and warmer stars, so that we were able to study both some of the different types of stars in the solar neighborhood. A lot of thought goes into the design of these. It's really impressive they work. There's so many things that could go wrong. I'm very impressed with my colleagues who get so many things right to be able to have instruments that are able to achieve this level of precision and stability. The instruments are inside vacuum chambers that are stabilized to millikelvin, millitorr stability in terms of the temperature and pressure to make sure that nothing moves. That even the expansion of your detector due to thermal variations at the millikelvin level matters for these types of observations. What does a spectrum from these spectrographs look like? Everyone looks basically like this at the big scale. If you zoom in, here you can see there's two streaks. There's the kind of lines. That's the stellar spectrum here of 51 Pegasi. And the dots, that's either a laser frequency comb or a Fabry-Pro fiber interferometer that are providing the calibration source. So we measure the starlight very precisely, but we also need to compare it to something. And so we now have atomic standards with laser frequency combs that make sure there's a grid of dots that we can compare as the starlight shifts. What is it shifting relative to? It's that grid of dots that we put on the detector just a little bit above or below our star spectrum. The instruments have gotten so good that now, instead of being limited by the stellar or the photon noise that traditionally limited us. Now the limiting factor is not the photon noise, it's not the instruments themselves, it's the stars. So previously we thought of stars as kind of these perfect light bulbs that were being Doppler shifted. But in practice, we now see that we can see active regions, so star spots and the plage and faculae around those star spots, those active regions rotating onto the disk, rotating off, coming and going on the left here. And then if we look at kind of make the movie on the right play, if you zoom in on the surface of the star, you see millions of these granules, little upwelling convective regions where hot gas is rising, starting to cool, and then falling back down. And as it falls back down, it's cooler, so not quite as bright. And that pattern, I mean, at the basic level, it averages out. Hot gas is falling, hot gas is rising, cool gas is falling. There's millions of these granules. It should average out. Yeah, it should average out. But at the level we're looking, we're starting to see the perturbations of this pattern on the solar spectrum. And so a lot of work now is going into how do we take these spectra, instead of just measuring one number, a Doppler shift, and maybe its uncertainty at each time, how do we extract the signals of the changes in the spectral signature, the line depths and line shapes changing in response to multiple different physical processes happening at the same time, and being able to subtract out the stellar signals to leave behind the planetary signals. And again, this is something that started with one or two students and is now blossomed into an effort where we have several grad students and postdocs trying to develop these methods. Again, this is something where we're bringing machine learning and scientific machine learning, AI techniques together, where we have time series data. But instead of being one number, the brightness of the star is a function of time, now it's a million numbers as a function of time. The brightness at every one of those pixels, different wavelengths of light, and now trying to reduce that data to a manageable level and understand what's happening on the star surface at each time, as well as the motion of the planet. So we have some big fancy models, but how do we know they're right? And so, in many labs, you're able to have controlled experiments where you do 12 petri dishes, the same thing, and you have a control set and a test set. Well, in astronomy, we don't get to control the stars. What we do get to do is look at different stars. So we're hunting for planets around many of our nearby stars that are interesting. But in most of them, we don't know what the truth is. We don't know the true motion of those stars. We're having to measure it. But there's one case where we know the motion of the star very well, and that's the sun. We know can send spacecraft to advance across the solar system because we have very precise knowledge of the sun's motion. And so these spectrographs that we've built during the nighttime, they're taking data on stars, and it's highly competitive to get that time. But during the daytime, there's no competition. There's only one star you can see. And that star is so bright that if you pointed the telescope, you'd ruin the telescope, the detectors, the instrument, it'd be a disaster. So we got support from the Heising-Simons Foundation to build a little bitty solar telescope and just stick it on the edge of the roof there and run a long fiber optic, so that during the daytime we can now take over 200 spectra of the sun every day, and we have this really large data set. Now it's up to like 160,000 spectra of the sun, so that instead of being in the regime where we have maybe 100 observations of a star, we now have 100,000 observations of the sun. And that's really important for these machine learning techniques, AI techniques that need a large data set to learn from. We're getting this large data set from the sun and using that to test our models, most of the time because we're dealing with the solar activity, the star spots that come and go, the granulation patterns. We've had a couple of fortuitous solar eclipses, and so Elizabeth Gonzalez is a grad student here being able to test our models at even higher levels of detail, making use of the fact that the moon blocked out parts of the sun during the data and gave us a whopping signal that's really hard to get right in detail, but allows us to refine our models because we have this even larger than usual signal to explain. And so these projects are sort of laying the foundation for a future mission that we hope will be able to characterize potentially Earth-like planets. And eventually we're going to use that to get light from the planets itself, take spectra of those planets. So now switching into the direct imaging mode where the planet is spatially resolved, taking spectra and looking at the differences in spectra from different planets, trying to do some comparative planetology of recognizing what's a bare rock, what's a big ball of gas that we can't see the surface in, what has oceans and continents rotating in and out of view, what has clouds that come and go over the course of a year, which ones have seasons as their orbital obliquities cause the ice cover on one hemisphere to change in the course of time. So these are the types of questions we want to do. And right now we're sort of beginning to get a little bit of practice on that. Not so much for the rocky planets, but for these giant planets. And so here, a case of one of the Kepler discoveries that subsequently became a target for the Hubble Space Telescope, and most recently the James Webb Space Telescope. And Jessica Libby Roberts, one of the postdocs here at Penn State, has been instrumental in being able to analyze those James Webb observations, detecting perturbations from an additional planet, sort of making the mystery of this planetary system even bigger. And these two planets are unusually low density. And so we call them super puffs, and trying to understand what are their atmospheres. And we can see it appears that they're likely enriched in some metals, but still trying to figure out exactly what those elements are in their atmosphere. While these missions are trying to study the atmosphere, they're going to have to observe not just for a night, not just for a day or week, but it's going to be many days, weeks, month of observing time, coming back to the same target when it's at a large enough separation to separate its starlight, trying to accumulate enough signal to noise to be able to measure the spectrum of that planet's atmosphere and maybe surface. And when we do that, we'll once again have a time series. We'll be coming back to these planets so many days, we'll be able to see the planet rotating underneath us. And if the planet is just a bare rock like the moon or Mercury, right, there won't be much variation. But if you were to look at the Earth, you would be able to see, as continents and oceans rotate into and out of view, the difference in the reflectance of the land, which reflects light relatively uniformly, versus the oceans, which reflect light in one narrow region, versus the clouds that are very bright and come and go. And so we do have hopes of determining which of these planets have an environment near a phase transition of water, able to support both liquid and gaseous water, for example. So that'd be a pretty exciting possibility from these missions as well. And again, the methods to do this are still in their early stages. So I've given a little bit of summary of the research we do. Before I close, I'll say a little bit about some of the fun things in terms of educational components. So we ask questions that are really curiosity driven. We find them interesting and we want to answer them. And we're using astrophysics and astroinformatics to try to combine modern astronomical data sets that have large volumes of data, trying to combine advanced statistical methodology. Sometimes they're computationally expensive, so we need high performance computing. And we do that in a science, astronomy, where it's really curiosity driven. We're not trying to, maximize profits or sell you the most ads or find oil or, any of these things that have ulterior motives that make it really hard to be totally objective and transparent. And so one of the great things about astronomy is we really have a culture of sharing data and methods because we're trying to work together. We're only going to have one of these missions across the whole world. It'll be an international collaboration. And so it's great sort of sandbox for preparing students for careers in science and industry where, maybe once they get to industry, they have proprietary data, there's health, privacy concerns, there's financial considerations, and the willingness to share data sets sort of rapidly shrinks as you get to some fields. But in astronomy, we really have this advantage. Their data sets are really large, open, and great for sharing. And that is really a key part of these large machine learning and AI type models that are really coming into prominence. And so it's great to have those as a training ground for our students. And then one final thing, sometimes I get questions from teachers about how they can get involved. And one thing I've done in many of my classes is a citizen science project. So there's a Planet Hunters project, started with Kepler, and now has moved on to TESS, where you're able to see actual spacecraft data that have been pre-processed and packaged in a way that humans can look for odd, unusual events. And you can just kind of draw a little box around transits you see. And as a teacher, it's a little bit frustrating because I can't depend upon the website to always be available. It's real science. Sometimes you can see yesterday when I grabbed a screenshot, it was like, all the data has been processed at the moment, come back later, right? And it's kind of convenient if you're teaching and you want like week 4 to have them do a project. But that's the nature of science. Is sometimes there's a need for people all over the world to put their eyes on new data and look for things. And then other times, people have already looked through it. We don't want to waste people's time. And so this particular project is a great connection to the work I do. But there's also many other citizen science projects. And so Planet Hunters is just one of the zooniverse.org project. If you go there, you can see there's a variety, dozens of just within the space category. There's also other sciences and even social sciences and translating ancient texts, and all sorts of cool stuff. And so while it might not be the best for like one class project where everyone's doing the same thing, if you have some precocious students who are looking for some opportunities to start getting a feel for what research is like, these are highly curated and set up data sets where people can make a difference. You often get started by just, doing what you're told. But then the real magic happens when people find something interesting. There's a page you can go and chat about it. And someone say, oh, like I found this interesting object. I wonder what it could be. And as things get, more and more people find them, people say, oh, sorry, that's just a binary star that's diluted by some extra starlight and looks like a planet. Good job, but, try again, right? And then, oh, this object's really interesting. We don't understand it. And so some of the Planet Hunter stuff have found things like quadruple star systems and things that weren't part of the standard planet search pipelines. They really are contributing interestingly. And again, for every one discovery that's made, there's hundreds of interesting stories that are great learning opportunities for whether it's students or teachers or just citizen scientists who want to find a way to contribute. There's lots of exciting opportunities here in many sciences. So if you haven't already, I encourage you to check those out and use them as a resource for students. And with that, I think I'll open up to any questions.
Thank you, Dr. Ford, for the wonderful presentation. I really appreciate you sharing those resources with our educators. I'll go ahead and get us started with the first question while we wait for others to send theirs in. So with the advancement of space telescopes and observational technology, how has our ability to detect and study distant celestial objects like exoplanets evolved over the last decade?
Yeah, so going back, I remember maybe 93, there was some excitement, 92, 93 about a exoplanet detection, and then it turned out to be a false alarm. And it turns out that's just, it's the first one that I paid attention to as a student, but there was a history of kind of exoplanet claims that then retracted. And then in 93, the first exoplanet discovery that stood the test of time came along. And so the first one was actually planets around pulsar, which is kind of like still an oddball today. And not long after, in 95, we got the first planet around a sun-like star. And that really ushered in an era where there was, at the time, we were limited by observational techniques and telescope time. And so very rapidly for about a decade, it was painstaking work and it took, people hard work and time, but it was kind of like we could make incremental improvements on the technologies we had, get more time, bigger telescopes, build more instruments that did similar things, and made rapid progress pushing down in terms of the precision. The first exoplanets had signals that were maybe at 100 meters per second, right? So you can't run 100 meters per second. That's fast. But today, most of the spectrographs that are active can detect planets down to sort of a 1 meter per second level pretty reliably. So 1 meter per second is what you need to detect sort of like Neptune-sized planets. Maybe if you have a lot of data in a cooperative star, you can get a little bit maybe to some super-Earth. But our goal for the true Earth analogs, Earth-size, solar-type star, habitable zone, that's closer to 10 centimeters per second. So we're still about an order of magnitude away from that. And there's been a lot of progress recently. I think in the best cases, we're getting down to maybe 60 centimeters per second. So on one level, another factor of 2 progress and represents a lot of hard work. But on the other hand, we're still a factor of 6 from finding these true Earth-sized planets in the habitable zone of solar-like stars, and so still lots of work to go. Some of our work on trying to test things on the sun, if I had to search for planets from the sun now, I think I could get another factor of 2 or so. But then there's a big question now of how well some of the techniques we developed for the sun transfer to other stars. And so one of the graduate students here, Evan Fitzmaurice, is beginning an observing program to pick one star and observe it very frequently and at high signal to noise and see if we can demonstrate some of the techniques that are working well on the sun, that they work as well on another star, and also there's some subtle differences between daytime and nighttime observations, and make sure that there aren't any surprises there. We're thinking of that as a prototype. If it works well on that first star, then it would be exciting we have the ammunition we need to write a proposal to justify future investment in observing many stars at the sort of high signal to noises and intensities that be necessary. There's several projects coming online. In addition to the new NHPF spectrographs I kind of talked about today from the Penn State group, there's several other great instruments, Espresso, the Europeans at European Southern Observatory, the Keck Planet Finder at Keck Observatories, the Terra Hunting experiment is trying to build a telescope in the Canary Islands, or an instrument for a telescope are existing in the Canary Islands. So the community is now at the point where we're sort of scaling up and building more instruments. And each of those is sort of a question mark of like, how well will we be able to go? And then
We have a question in the chat. It says, how do space telescopes focus on observing a distant object while orbiting in space? How is the picture taken stable? How far away is the Hubble ST?
when it passes overhead, it's closer to you than other cities that you could drive to in a few hours, right? So the Hubble Space Telescope is very close to us. The distance to the other object is basically always effectively infinity for focusing your telescope. So that you don't really need to worry about focusing, distance changing. There are issues with the spacecraft in orbit around Earth is changing its temperature. So the sun is heating one side, the other side is cooling to space. So you have thermal expansion of the telescope and optics. So it is a challenge to keep in focus, but really because of the thermal transients. That's one of the factors that has driven some of the recent telescopes like James Webb to not be in Earth orbit, but James Webb is at one of the Lagrange points of the Earth-Sun system, so it's in a stable environment, has this big solar shield kind of constantly blocking out one side from the sun. Yeah, so that sort of deals with a lot of the thermal transients. There's still some as you point this telescope different ways, but dramatically better than a telescope like Hubble or TESS that's in an Earth-type orbit.
I'll ask another question. You already talked about this a bit, but are there any upcoming missions or projects that you're particularly excited about that you could share with us?
Yeah, so I mean, there's at one level, it's always easy to want more, but at another level, it's kind of amazing how many space missions are operating right now. So we talked about the Kepler mission, which is wrapped up, the TESS mission, which is its successor. The Europeans are planning the Plato mission. So the Plato mission will kind of be something in the middle. It will be able to point at specific regions and stare for a while and be able to go longer than TESS does, but still cover large fractions of the sky. And so it's aiming to try to help us with these questions of finding Earth-like planets around brighter stars. And so that'll be quite exciting. NASA's planning the Raman Space Telescope. The Nancy Grace Raman Telescope is making use of a mirror that was available from the National Reconnaissance Office. And it's a very high quality mirror, and so it's being used to test some of the capabilities of direct imaging. So before we build a ginormous space telescope to do the highest contrast imaging, looking for faint little stars next to really bright stars, it's always good to test these things out at a smaller scale. And so it's providing that opportunity with a direct imaging test bed, but then also as part of it, it's going to be able to do sort of a transit study looking towards the galactic bulge and looking at parts of the galaxy that were sort of beyond the scope of Kepler, look for differences as different locations in the galaxy, and also microlensing. So I talked about a couple of, I guess, 3 methods. There's direct imaging, transits, and radial velocities, and each method sort of like technology provides some limits, and so each has a sweet spot where they're able to see planets best, and there's sort of a gap between the radial velocity planets and the direct imaging planets where we don't have a lot of good data now, and so connecting those two is quite challenging. And microlensing, that the observing of a star's light being lensed by a passing star in front or a passing planet in front will allow us to probe sort of the regions of like a few AU that are really hard to probe with other methods, and so will help us connect some of the populations discovered by transits and radial velocities to the planets being discovered by direct imaging surveys, and so that's going to be pretty exciting for demographics. And another one that I'll mention is the European Space Agency ran the Gaia mission. The mission itself has wrapped up in terms of the data collection, but the analysis is an enormous puzzle. They've been plotting the position and motion of billions of stars in the galaxy, and in addition to studying the stellar orbits in the galaxy and galactic structure, that are also going to be capable of detecting planets around stars by seeing the wobble of the star, but instead of it wobbling towards and away from us using the Doppler effect, wobbling in the plane of the sky using its precision astrometry techniques. And so that data set, we've seen some of the early Gaia data releases that were able to measure the distances of stars and get their brightnesses and lead a really revolution in our galactic astronomy archaeology within the galaxy. And the next data release from Gaia, the next processing, they're going to be able to help us get the position of stars at individual epochs so precisely. We'll be able to get out a large number of planets, probably primarily giant and Neptune mass planets, but still very interesting from the planet formation perspective of, again, probing a different niche or parameter space, these giant planets at orbital periods of, say, 1 to 10 years will be sort of the sweet spot for Gaia, and very complementary to our current data sets. And so I know a lot of astronomers are really excited about that upcoming data release from that mission. And it really points to how some of these missions, the mission's been running for over 10 years, wrapped up, and there's still exciting just getting the data release out for people to begin doing science of. A lot of these missions provide stuff that lasts for decades after the mission wraps up. And so, yeah, lots of exciting things happening, and of course, many more discoveries with the James Webb Space Telescope happening as astronomers are studying both the giant planets at high signal to noise and being able to characterize things like the atmospheric composition and thermal temperature pressure profiles of these planets, and in some cases pushing to rocky planets and being able to determine that there's so little reflectance the planet must be primarily rocky. Some thoughts being able to discriminate between different mineral compositions. Recently had a visitor here talking about some of their exciting work there. So there's lots of exciting things happening, and it's just so many cool things happening. You have to, unfortunately with science, you have to become an expert in like one sub field to make any progress. And so we sort of enjoy hearing about our colleagues' cool projects, even though we know each of them takes years to make happen. Getting the kind of highlight reel, such as I try to give you for you here, can make it really fun to hear all the exciting things from different missions happening at once.
Very cool. Thank you. I love hearing about all the advancements that are happening and what's to come. We did get one more question in the chat. It says, as teachers negotiate the new PA Steel standards, which are highly focused on science and engineering process skills over actual science content, I'm curious what you see as your needs and wants in terms of preparation of students for advanced studies. What can schools do better to prepare students for a future in science?
Depending on the day, I can be extremely optimistic or extremely pessimistic. So yeah, there's both good things and challenges in terms of the situation in the schools. I think on the plus side, there are opportunities for students to learn things, whether it's through all the materials that are available on the internet. You can find scientific papers, you can find blog posts breaking down a scientific paper. So there's a lot of opportunities. So if you do have some students that are able to kind of go beyond your required curriculum and have some enrichment activities, I think one fun site I might point you to is Astrobite. It's where graduate students typically are summarizing scientific journal articles. So they're kind of taking the long, detailed version and bringing it to a one-page blogish type format that's navigable for either another graduate student or a citizen scientist just interested in learning. That might be a nice middle ground that you can expose people to start see how actual science is happening. That's probably not in the curriculum because the paper probably came out in the last month if they're writing a summary of it, right? So it has both the excitement but also the intractability of integrating into a high school curriculum. In terms of the things the students come with, we see, if I ask how do the graduate students in our research groups spend a lot of their time, the reality is a lot of it is in data analysis, coding. And so yes, there is that foundational physics to provide the framework for interpreting the results, but in terms of their first research projects, it's probably going to be extremely computer skills driven data analysis. And so if there are opportunities to fit in some basic coding skills to work with analyzing data to support some of the standards as opposed to only pen and paper solving problems that can be solved analytically, I think that would be a nice thing to see, because a lot of students do find it. Like, one of the things I tell the undergrads is, when you're deciding to apply to graduate school, the most important thing is that if you like doing research, because it's a very different style than, even the undergraduate training is still very much fundamentals based, and they're mostly solving problems that can be solved pen and paper. And while that's an important element, it's not the majority of what the professional scientists are doing on a day-to-day basis. And so it's important that people get experience working with real data, doing data analysis, making models that can coding to implement a physical set of equations into a numerical computation. And so maybe some of those can be integrated to help provide a bridge towards the first research experiences. On the plus side, the college level, there's a lot of efforts to get students involved in research pretty early on. sometimes really early on, first, second year college students are trying to integrate to a research group, and the more they have those computer skills when they arrive, the more practical it will be for them to get something out of those experiences.
Thank you so much. Great answer. I think with that, we'll go ahead and close the Q&A session. And thank you, Dr. Ford, for being here, sharing your wonderful insights with us. Thank you to all the educators and teachers in attendance today that were listening. I will put a post survey link in the chat too, if you guys don't mind educators taking a second to do it. It just allows us to better tailor these webinars for you all. So thank you, everyone again. We hope you enjoyed, and we look forward to seeing you guys next time.
Thanks so much to CE.
Thank you so much. I would like to extend a special thank you to our sponsors for supporting us and making these cost-free webinars possible for you all. I would also like to thank all of you in our audience today for attending the webinar. We hope you enjoyed it. I kindly ask that you take a minute to fill out our post-webinar survey. Your feedback makes it possible for us to serve your needs. The links to the surveys will also be emailed to you so that you can complete it at your leisure. Thank you again to our speaker, Dr. Ford, and to you all for joining us today. We will send you a notice when the recording of today's webinar is available. Be sure to be on the lookout and register for future events. We'll see you next time.